assignment 4, and at the same time beginning your review of the sample exams, because you don't have a huge amount of time between the last class and the final exam to study. But you already know that the final exam for this course will be mostly made up of questions that are on those 11 sample exams that I've given you. So if you can handle all 275 questions on those exams, then great, you should do very well on the final exam for this course. Okay, so we've been talking about random variables and their expected values. And now I'm going to introduce you to a technique that we use when trying to compute expected values. It's very useful. And it involves using linearity of expectation. So if you remember, linearity of expectation said that the expected value of x plus y, it's this kind of divide and conquer thing that says, well, if we have a random variable that's made up of the sum of two random variables, then we can compute the expected value of that thing if we can compute the expected values individually. And more generally, the expected value of x1 plus x2 plus xn is just the sum of those expected values. And this is extremely useful because it works for any random variables. You don't have to assume anything about them. They don't have to be independent or anything like that. And it somehow looks like it's making the problem simpler because you have expected value of some complicated random variable that's the sum of all of these things, and you can reduce it to finding these individual expected values of these things. And it's really good if these are really simple. And the technique of indicator random variables is to make these things the simplest things you can imagine. They're just, an indicator random variable is just a random variable which always takes on the value 0 or 1. Okay? So whatever your experiment does, this indicator random variable x will take on the value 0 or it will take on the value 1. That's all. I mean, this is the definition of indicator random variable, and this is the critical part here, that the range of the random variable is 0 or 1, or if you like, you do the experiment and x always maps onto to 0 or 1. And one of the reasons they're so nice is it's really easy to compute the expected value of an indicator random variable. So what is the expected value of some indicator random variable x? Well, it's just equal to the probability that x equals 1. And so why is that? Well, we've seen that the expected value of x is just the sum over all the values that x can take on, little x, of little x times the probability that x equals x. But in the case of indicator random variables, this sum is really simple, right? There's only two different values that x can take on. So we get one term which is 0 times the probability that x equals 0, and another term which is 1 times the probability that x equals 1. Well, this is 0, and this is 1 times something, so this is just the probability that x equals 1. Okay. So it doesn't get, at least in terms of random variables, it doesn't get any simpler than this, right? You only need to figure out one thing. What's the probability that it's equal to 1? And you'll get the expected value of that random variable. And so very often we can have a really complicated looking process, some complicated random variable, and it happens a lot in computer science because the sort of questions that we ask are about things like algorithms and their running times. And the running time of an algorithm really is asking how many instructions does this thing take when it runs on a computer. And well, so usually that maps back to lines of code, and you ask, okay, how many times does this line of code execute? And well, you define a random variable that says, if during the ith step of the algorithm this line of code executes, then we'll say that this random variable is, this indicator random variable is 1 if it executed and 0 if it didn't. And then the number of times that line of code executes is just the sum of those indicator variables. So we'll see a couple of examples of that in a minute. But for now, let's look at an easy example that we wouldn't really know how to solve prior to today. So let's work in this following experiment. We'll say R is equal to R1, R2, R3, up to Rn is a random bit string. So that means our set of outcomes, the bit strings that we can have, is this sequences R1 up to Rn, such that Ri is in the set 0, 1 for each I and 1 to n. Okay, so when I say R is a random bit string, I mean really we run this experiment. So we have this sample space, which is all the bit strings of length n, and the probability measure, so how many bit strings of length n are there? No, it's not a trick question. 2 to the n. And the probability measure over this thing is going to be probability of any particular bit string is just going to be 1 over 2 to the n. Okay? And that's for each bit string. Okay. All right, so an easy question to ask, but we've done it already, is, well, what's the number of 1 bits in this bit string? And we saw you can do that with linearity of expectation quite easily. And then there's some obvious indicator random variables, which is, these are the indicator random variables themselves. In fact, R1 is the indicator random variable. But let's think about something harder. So a run is a sequence that looks like this. So you have Ri is equal to Ri plus 1 is equal to Ri plus 2 is equal to, and so on, up to Ri plus, let's say, k minus 1. And that is a run of a length k is this kind of thing. So you write down your bit string. Right, this is R1, R2, R3, all the way up to Rn. And where are the runs here? Well, for example, here is a run of length 3. Right, this is Ri. That's equal to Ri plus 1, and that's equal to Ri plus 2. Here is another run of length 3. These 3 1s in a row. This is Ri plus 1, Ri plus 2, and so on. So that's what a run of length 3 is, and in general, a run of length k is You just have k things in a row that are all the same value. Okay. All right. So let's ask, let's say x is equal to the number of runs of length k. So for example, in this one, if I take k equals 3, then how many runs of length 3 are there? Well, there's 3 ones here, so there's one of them. There's 3 zeros here, so that's a second one. That's a run of length 1, a run of length 1, a run of length 3 again. So that's a third one. And finally, a run of length, this is just length 1, another one of length 3, so that's a fourth one. So in this case, the number of runs of length 3 is 1, 2, 3, 4 in this example. Yeah?
If we had a run of length 4, would that count as one run of length 3 or 2 runs of length 3?
Counts as 2 runs of length 3, right? So if we look carefully at the definition, so for example, here's where things get really bad. If I have this, then I have, this is a run of length 3. This is also a run of length 3. This is also a run of length 3, and so on. Okay, so if you have a run of length longer than 3, that gives you many runs of length 3. It's in fact whatever the length of that thing is minus 2, I guess. Yeah. So x is the number of runs of length k, and I would like to know what's the expected value of x. And this is somehow an important question for gamblers, because a lot of games in casinos, for example, if you play them optimally, so games like blackjack, you win almost half the time. You win like 49% of the time. And you lose 51% of the time. And so you can think of, well, you can make a bit string out of that where 0 means I lost and 1 means I won. And then one mistake that a lot of people make is to come up with these surefire strategies to always win at the casino. And one that you'll see is the doubling strategy. Anybody seen that one before? Yeah, it's not a good strategy. And the reason it's not a good strategy, so the doubling strategy says, well, I will bet $1 on a hand of blackjack. And if I win, good, I have won $1. And if I lose, well, I'll play again, but this time I'll bet $2. And then if I win that second hand, then I will have actually won $1 by the end of this process. I bet 1, and then I lost it, and then I bet 2, and I won 2, so I'm ahead by 1. And if I lose twice in a row, then on the third game, I'm going to play $4. And if I lose 3 times in a row, then on the fourth one, I'll pay $8. So that's called the doubling strategy. And you can check that if you play this game and you stop the first time that you win, you'll leave with $1 more than you left with. Sounds perfect, right? What's the problem? The problem is, well, you have to be willing, I mean, for this to work, you have to be willing to bet arbitrarily large amounts of money. And so what people underestimate is the probability that they will lose 5 games in a row or 10 games in a row, right? After playing 10 games, understand then, well, okay, what is it really possible? Could I ever lose 10 games in a row? And so a good model for that is, let's say, these perfectly random bit strings, which are they're sort of optimistic, because I said that you win about 49% of the time in blackjack and you lose 51% of the time. But even if you won 50% of the time, that's sort of what this models. So we're interested in these runs, maybe a number of times you of length k, and we'll look at the expected number of these things. And so as k gets big in this gambling procedure, that's when you're putting lots of money on the line. How many times would you have to do that if you played over the course of n games? Okay. So I want to know what the expected value of x is. Looks hard, right? So since this is a lecture about indicator random variables, we should think about, well, can we break x down into simpler things, little indicators? And usually the clue is when someone asks you, what is the number of times something happens? That usually means there's an indicator variable that you can define for each time that it happens. So let's define for each of these integers I in 1 up to n minus k plus 1, we'll define xi is equal to 1 or 0. So it's going to be an indicator random variable. And it's equal to 1 if Ri is equal to Ri plus 1 is equal to Ri plus 2 is equal to Ri plus k minus 1. So in words, that means a run of length k starts at position I. And if that's not the case, then the value of this thing is equal to 0. So x is the number of runs of length k. Xi tells you, for example, x1 tells you, is there a run of length k that starts at position 1? x2 tells you, is there a run of length k that starts at position 2? x3, is there a run of length k that starts at position 3? So x is actually equal to the sum I equals 1 up to n minus k plus 1 of xi. Right? If I want the number of runs, x, then I just add up all of these things that tell me whether a run starts at position 1, whether a run starts at position 2, whether a run starts at position 3, and so on. Okay, so that means that the expected value of x is equal to the expected value of this sum of xi. Because x is equal to xi, so the expected value of x is equal to the sum of the xi's. So the expected value of x is the expected value of the sum. Okay. What should we do next? So we have expected value of a complicated sum. Yeah?
Do a sum of
Yeah.
expected values.
So now we use linearity of expectation. Remember, this is the expected value of x1 plus x2 plus x3 plus x4 all the way up to xn. And linearity of expectation says that that's equal to the sum of the expected values. And this is always the recipe that we use. We take the thing we want to know, x, we break it up into indicator random variables so that when you sum those, that's the same thing as x. Then you get the expected value of x is the expected value of the sum. And now we use linearity of expectation to say, look, we only need to now compute individually each of these expected values. And the nice thing is, these are really simple random variables. xi is either 1 or 0. If we want to know its expected value, we just need to know the probability that it's equal to 1. Okay. So what does it mean that xi is equal to 1? Well, that means either that Ri is 0, and then we have k minus 1 more zeros coming right after it, right? So Ri plus 1, Ri plus 2, and so on. Or Ri is equal to 1, and then we have k minus 1, 1's coming after it. That's what it means for xi to be equal to 1. It means Ri is the first thing in a run of length k, so it could be a run of zeros, or it could be a run of 1s. All right. So we can write that lots of ways, but here's one way to rewrite this. This is the same thing as saying that Ri plus 1 is equal to Ri, and Ri plus 2 is equal to Ri, and Ri plus 3 is equal to Ri, and so on up to Ri plus k minus 1 is equal to Ri. Just another way of writing that, maybe writing this in some concise way. That basically, all of these things are equal to the first one. All right, what's the probability that this happens? So there's lots of ways we can proceed here. We can directly count the number of bit strings and divide by the total number, or we can remember that in these random bit strings, the bits themselves are independent. So somebody want to tell me the answer? Yeah?
Is it 1 over 2 to the I plus k minus 1?
So there's no I in there, but there is a k minus 1 in there, right? This is how many, this is the intersection of a bunch of events. How many of them? We're counting from 1, 2, 3, up to k minus 1. So this is 1/2 to the k minus 1. So Ri plus 1 equals Ri. The probability that that happens is equal to 1/2. Ri plus 2 equals Ri. The probability that that happens is equal to 1/2, and so on. And those are actually independent events, because Ri plus 1 is independent of Ri plus 2, which is independent of Ri plus 3, and so on. Or if you like, you can count exactly how many bit strings there are like this, right? So how many bit strings are there like this? Well, this bit string has k of its bits fixed at 0. So the number that are like this is 2. So all the other bits still have choices, the n minus k bits. So there's 2 to the n minus k bit strings that look like this. So there's some stuff before and some stuff after. And there's 2 to the n minus k bit strings that look like this. So in total, the number of bit strings that look like this or look like this is 2 to the n minus k plus 1. And the probability that we get one of those bit strings is that thing over 2 to the n, the number of bit strings, which is 1 over 2 to the k minus 1. So there's different ways we can proceed depending on whether we prefer to use probability or just straight up counting, but we'll get the same answer both ways. So expected value of xi is 1 over 2 to the k minus 1. That's nice. It doesn't even depend on I. And so now we're done, right? So this thing here is the sum. I equals 1 to n minus k plus 1 of 1/2 to the k minus 1. Well, there's nothing, I mean, what's in here doesn't depend on the variable I, so all we have to do is count the number of these things. Here we're counting from 1 up to n minus k plus 1, so this is equal to n minus k plus 1 times, or divided by 2 to the k minus 1. So that's the expected number of runs of length k. And if you like, just to get a feel for this, when is this big and when is this small? Well, if I take k is equal to 1 plus log base 2 of n, then this thing becomes n minus log n. That's what's on top. On the bottom, this is 2 to the log n. So this is n. And so I get 1 minus log n over n. So this is like just about 1, right? I mean, as n gets big, log n over n is small. So it's just about 1. If we think back in terms of gambling, well, that means that if I play, for example, 128 hands of blackjack or some fair game, and I ask, what's the expected number of runs of length 8? So how often do I expect that it happens that I lose 8 times in a row? Well, actually, that number is pretty close to 1. So play 128 games of blackjack. That does not take long at all in a casino. They're very efficient. There will be, even if you're playing the best you can, even if you're beating the odds, there's still a reasonable, well, it's still the expected number of times that you will lose 8 times in a row is very close to 1. So in particular, that means there's a reasonable chance that you'll lose 8 times in a row. And 8 times in a row, if you were starting with $1 bets and using the doubling strategy, you better have $256 ready to cover that. Actually, $512 if you've lost. The 9th bet is worth $512. Yeah?
That's the same probability that you win 8 times in a row?
Well, if it was a fair game. It's actually not a fair game. But yeah. But with that doubling strategy, winning 8 times in a row doesn't really help you much, right? If you lose 8 times in a row, you've lost nearly $512, and nearly lost $511. If you win 8 times in a row, you've won $8. Down into these indicator random variables, and somehow becomes easy. Okay. Here's another example. Let's say I have n people, and d days in a year. Okay, let's call the people person 1 up to person n. And this is one of these birthday questions, so each person is equally likely to be born on any given day of the year. B usually we think of as 365, but soon we'll be living on Mars, where the number of days in a year will be different, so it's better that we figure out how to solve that now. And so the birthday paradox asked us, well, what's the probability that at least 2 people have the same birthday? But we can ask similar questions in terms of expected value. And let's say, what is the, or let's define it really carefully. X is equal to the number of pairs ij in 1 through n such that pi and pj have the same birthday. Okay. And now I'm going to ask you about the expected value of x. Now, from the birthday paradox, we know that when you have 23 people and there's 365 days in a year, there's probability is slightly bigger than a half that at least 2 of them have the same birthday. And that was non-trivial, right? We had to look at the complementary event, do some careful counting, and then all we got was a formula with this annoying factorial in it that we couldn't easily understand even what that meant. We saw that we could use some approximations on it, but that wasn't easy. So let's see if looking at the expected value, so the expected number of pairs that of people who have the same birthday, whether that makes it any easier. Okay, so I have this complicated random variable x, tells me the number of pairs ij such that pi and pj have the same birthday. I would like to express this as a sum of simpler indicator random variables. So any suggestions for what one of these indicator random variables should look like? So the nice thing is we can do whatever we want. And here we can almost read it off of this thing. It's the number of pairs ij such that pi and pj have the same birthday. So let's just say we'll define an indicator random variable xij, which is equal to 1 if pi and pj have the same birthday. And it's equal to 0 otherwise. Then, what do we have? Well, what's x? For x, all we have to do is add up all of these indicator random variables. So that's just, we take the sum, I equals, let's say, 1 up to n minus 1. J equals I plus 1 up to n of xij. Right? This is think of this as 2 nested loops, one running over I, the other one running over j, and it will consider every pair ij exactly once. Right? So, in fact, it treats the ordered pairs ij where I is less than j, so everything in here will be considered exactly once. And if those people share the same birthday, then we add 1 to the number of pairs of people who share the same birthday. So this exactly counts the thing we're interested in. So that means the expected value of x is the expected value of this sum. what should we do next? So I want you, this is really a recipe book stuff. I want you to know, follow the recipe. So we have a complicated random variable x. We express it as the sum of indicator random variables. That means the expected value of x is the expected value of the sum. And what's the next step? Yeah. We take the sums out or bring the expected values in. So the expected value of the sum by linearity of expectation is just the sum of the expected values. So this is a huge thing, right? There's n choose 2 terms here in this sum, but we can just pull in, take the expected value of each of those terms individually. So this is just the sum I, sum of the expected value of xij. And then this is where we pause because we know what's coming next. The next thing is we need to know what this expected value is so we can put it in this formula. So we go back and we remember, okay, what was the definition of xij? Definition of xij is pi and pj have the same birthday. So the expected value of xij is equal to the probability that xij equals 1, which is equal to the probability that pi and pj, pi and pj have the same birthday. So I take two different people, me and one of you. What's the probability that we have the same birthday? Yeah, it's 1 over 365, right? So there's, I mean, the easy way to see that is I have some birthday. What's the probability that your birthday is the same? Well, your birthday is one of the 365 days of the year, and only one of those is my birthday, so it's 1 out of 365. Yeah? Here? That's I plus 1. So this is just a way of counting all the pairs ij without repetitions, right? Okay, so this, the probability that two people, just two specific people have the same birthday, is just 1 over the number of days in the year. I mean, if you don't trust that, you can also go back to the full counting, all of the different possibilities. So this guy has d possibilities for his birthday, and this guy has d possibilities for his birthday. So that's d squared possibilities. How many of those are there where these guys have the same birthday? Well, this could be, this one was born on January 1, and this one was born on January 1. This one was born on January 2, and this one was born on January 2. So then you do that, you'll get d over d squared as your answer, which is 1 over d. Okay. All right, so that says that this thing is just the sum. I equals 1 to n minus 1. J equals I plus 1 to n of a 1 over d. But this double sum here, I mean, it's just designed so that I consider each pair of people, person I and person j, and I don't miss anybody and I don't count anybody twice. Well, what's the number of pairs of people if there's n people? N choose 2. Okay. And we want to be long handed about that. That is n squared minus n over 2d. So why is this more useful than the answer we had before? Well, I'm interested in, the birthday paradox is interested in the case where you get something close to 1 here, right? Where you hope that you have a reasonable chance that the number of pairs is at least 1, so that the number of pairs of people who have the same birthday is at least 1. So in particular, there's a pair of people who have the same birthday. And this says, well, actually, on the bottom you've just got this d down here, and on top you've got this n squared. And so if you think, okay, well, 23, so that means that I've got, with 23 people in a room, this is like 23 squared. This is 700 and something, 2 times 365. So you start to see, okay, why 23 is enough. And if you plug this in with n equals 23 and d equals 365, you get 23 choose 2 divided by 365. That is approximately 0.69315, something. Okay. So if I take 23 people in a room, the expected number of pairs who have the same birthday is a little bit more than a half. So that kind of jives with what we expect, right? Because we sort of said, before we were looking at the probability that there's at least 1 pair. So sometimes there's 0 pairs. Roughly half the time there's no pair who has the same birthday. And sometimes it's more than that. It's at least 1. So this kind of matches up with what we expected there. But I think more importantly is this formula here that lets you see why this happens so fast. Why this happens with only 23 people. It's because there's this many pairs of people. Right? So the question is about pairs of people. This is the number of pairs. So it's about n squared, or 23 squared over 2. So the number of pairs grows much faster than the number of people. So for example, if you worked really hard on assignment 3 and you struck day, I suggest you try and do the same thing we're doing here, but with triples instead of pairs, and you'll see it's really easy, much easier than the assignment question. And you'll get almost the same information that, yeah, right, there's some magic number where it's pretty reasonable that you get 3 pigeons in the same hole. The expected number of triples in the same hole becomes reasonable, close to 1. Okay. All right. So that's some toy questions. Let me do a really computer sciencey one. So, anybody seen the insertion sort algorithm before? Some of you. All right. So it looks like this. For I equals 1 to n, j equals I, and while j is bigger than 1, and a at j minus 1 is bigger than a at j, swap a j with a j minus 1, and j equals j minus 1. That's the whole algorithm. And it works like this. So starts counting I equals 1 to n. So that's the array indices 1, 2, 3, 4, 5, 6. First time through, nothing terribly exciting happens. I equals 1, then j equals 1, but j is not bigger than 1, so the while loop doesn't execute. Second time through, this is I. It's pointing at 5, so I is 2. Then j is also 2. And this while loop says, yeah, 2 is bigger than 1. So let's compare these two elements, a at j minus 1 and a at j. That's 1 and 5. And 1 and 5 are in the right order. So a at j minus 1. So 1 is not bigger than 5. So the while loop ends. Nothing happens. Third time through, this is where I is pointing. I is 3, and j is 3. 3 is bigger than 1. So we compare these two things. And we realize that 5, which is at position j minus 1, is bigger than 2 at position j. So we swap those things. Decrement j. And now we do the same test again. Is 1 bigger than 2? No, it's not, so we stop. And we move on to the next thing, which is 7. First time through the loop, 7 is bigger than 5, so we immediately stop and move on to this thing. First time through the loop, 3 is smaller than 7, so we swap these two. Now j is pointing at 3. 3 is smaller than 5. Swap those two. And now 3 is not smaller than 2, so we stop. And then finally we finish off with I over here. Last iteration of the outer loop. Swap 4 and 7. Swap 4 and 5. And we don't do anything to 4 and 3. We stop, and the whole array is sorted. So it's called insertion sort because it's really growing a sorted array from left to right. So once we're at position I, all the elements A1 through AI minus 1 are already in sorted order. And we're just looking to see where should we insert this thing, this new thing that we're looking at. So we slide it over until it fits in the right place. So, nice thing about this algorithm is it's very simple, right? There's a for loop that counts from 1 to n. We know how long that takes. It executes n times. There's this line of code which executes every time you go through this loop. So we know how many times. So this executes n times. This one also executes n times. Then there's this while loop, which has a complicated condition. I don't know how many times that executes, but maybe more interestingly, and completely related to this, is this thing here. How many times does this happen, and how many times does this happen? So what's the best thing that could happen? What's the best kind of array I could give this where this thing would run really, really fast. If the array is already sorted, like this one, then it'll look at 1, do nothing, look at 2, realize it's already bigger than 1, do nothing, look at 3, realize it's already bigger than 3, do nothing, and so on. And in fact, for a sorted array, these things never execute. So we never need to swap anything because everything's already in the right order. So what's the worst thing that can happen? So the worst thing that can happen is the array is completely reversed, so it looks like this. And when that happens, by the time we get to here, this is already sorted, but this new element that we're looking at is smaller than everything we've seen, so it's going to have to swap to here, to here, to here, all the way to the beginning. And when that happens, so this is a swap, this swap thing happens n choose 2 times, because every pair of elements is in the wrong order. So if I look at 2 particular elements, is there ever going to be a time when they swap? There has to be, because by the time this thing finishes, they're in the right order. So at some point, the smaller one came closer to the front than the larger one. And that had to happen for every pair. So this line of code executes somewhere between 0 times and n choose 2 times. Big difference, right? So, you might ask, okay, let's say, let A be a random permutation of 1 to n. So suppose the input array is neither perfectly sorted nor reverse sorted, but it's a random permutation. That seems like a reasonable kind of input. Maybe somebody gives you random stuff, a reasonable model to assume. And now you ask, okay, let's x is the number of times line, we might as well say 4 executes. What is the expected value of x? This is a real computer science problem here. It's a sorting algorithm. It doesn't get more computer science than that. We're actually looking at lines of pseudocode, which these are almost lines of Python code, if you like that. And I'm asking you very specifically, how often is this thing going to execute if the input is random? It looks complicated, right? We know somehow the answer is between 0 and n choose 2, but that's a pretty big range. All right. So x is a big, complicated, random variable that counts the number of times that line of code executes. Any idea how to break that down? Yep.
You could have indicator variables for each iteration of the loop, so whether or not that line executes.
Each iteration of what loop, though? So the outer loop is good. I mean, we know the outer loop is easy to understand. It executes exactly n times. But that inner loop executes a variable number of times. So that's not, it's not even, like we need to define some specific set of indicator variables, and the number of those, I mean, hopefully shouldn't be random. That would be difficult to study, at least for this course. So this is one of those ones where there's actually a trick that once you see it, it becomes completely trivial. But if you don't see it, this looks really difficult.
say one number and one number.
Yeah, so it looks at two numbers and says that one is bigger than the other and they're in the wrong order. So if they're already in the right order, then they will never get swapped, right? So notice, as you watch this thing execute, if I have something like, it got to here, and over here is the number 15. Maybe there's some stuff in between. But I know now that 15 and 7 will never swap, right? They'll never change positions because changing position only happens, whatever happens with 15, it moves one space closer to the front each time, but it'll never get past 7 because to get past 7, it gets compared with 7, and they're in the correct order. So if we just think about what that means over all the pairs of numbers, so for each of the n choose 2 pairs x, y in 1 to n, with x not equal to y, define an indicator variable. I'm going to call it I for indicator, xy, to be equal to 1 if x and y get swapped in line 4, swaps x and y in line 4, and 0 otherwise. So let's really convince ourselves. Every time it executes, it swaps something, right? Now, if it swaps two things, like for example, line 4 executes, and maybe we had a 6 here, line 4 executes and it swaps these two things. So 6 moves over here, 7 moves over here. Will it ever swap them again? Will it ever swap 6 and 7 again? That'll never happen, right? So in particular, because once they're swapped, they're in the right order, so that they won't get in the wrong order again. So that says, well, the number of times line 4 executes is, well, each time it executes, it swaps a particular pair x and y, and it'll never swap them again. So I think that means that the number of times line 4 executes is exactly the number of pairs x and y that are swapped. So x is exactly the sum I equals 1 through n, j is I plus n minus 1, j is I plus 1 up to n of the indicator variable, oh, let's not call these x and y, the indicator variable xy. So we sum over all the pairs in the input array, and we look to see if the algorithm swaps that particular pair. Yep.
Still y equals
It should be y equals x plus 1. This thing here, sometimes if you want to be concise, you might write something like x not equal to y, where we know that these range over 1 to. But this is basically all the pairs x and y counted exactly once. Okay. All right. So what's the next step? Well, we want the expected value of x, which means we want the expected value of this thing. And what happens next? what always happens next? Yeah. We use linearity of expectation. We get this sum with an x, the sum with a y. We get this thing, and this is just shorthand for whatever I've written in here. The expected value of this thing. So now we go back and hope that we defined an indicator, a random variable, that's easy to figure out its expected value. But let's think about this for a minute. This says I take a particular pair of values, x and y. Right, so A is supposed to be a permutation of 1 through n. So I take x, some x and some y, and 1 through n. So maybe I take 5 and 17. And I ask you, is the algorithm ever going to swap 5 and 17? So when does that happen? Well, our sum does it nicely because when we sum this way, we always have x is less than y. So we have x less than y. So in our input array, it might be that we have x here and we have y there. Is the algorithm ever going to swap x and y in that case? No. On the other hand, if we have y first and then we have x, is the algorithm going to swap these things? It has to. There's no way around it. If it's going to sort properly, y has to come after x in the end. And the only way these things can pass each other, because the only thing the algorithm does is swap consecutive elements, is to be swapped at some point. Okay. So, all right. So let's. Where's our indicator? Variable. If the algorithm swaps x and y in line 4. So another way of saying this is to say, if x is less than y and y comes before x in the input array. That's all we're saying here, right? Y comes before x, then we'll do the swap, otherwise we'll leave those two alone. All right, so I have a random permutation and I have two particular values. What's the probability that x comes before y? What's special about x? What's special about y? Nothing, really, right? There's no reason x should come first, come before y in a random permutation, and there's no reason y should come before x. So that probability is going to be a half. So now we're done. Well, the expected value of this thing is just the probability that it's equal to 1. And the probability that it's equal to 1 is when y comes before x. And that's probability 1/2. And now x and y here, they're just summing up over all the pairs of n choose 2 pairs of values. So this is n choose 2 times 1/2. And if you want to write that out longhand, that's, what is it, n squared minus n over 4. So it's not an awesome algorithm. Right, remember we said the number of times could be 0, or it could be all the way up to n choose 2. Well, it's exactly halfway in between. So that's pretty big. It's not a super fast algorithm. Okay. So I think this is a really interesting example because it takes something that looks like really difficult to figure out, and in the end it boils down to nothing. Just an easy observation, and then you're done. All right, let's look at another algorithm. Even simpler. Finding the max in an array A of length n. So here's sort of the thing you may have had to implement in a first year programming course. You do something like, I'm going to guess that the maximum is equal to minus at infinity, and then say for I equals 1 through n, if A at I is bigger than the current value of the max, then the new max is A at I. Once all of that is done, I return the max. Basic thing. And if we want to analyze the running time of this thing, and this one is dead simple, right? There's one line that executes once. There's this for loop that executes exactly n times. We pass through it exactly n times. There's this if statement. This condition is checked every time we go through the for loop, so exactly n times. And then there's one line here that may or may not execute. Sometimes it does, sometimes it doesn't. So of course, we have to ask the hardest question we can ask. So if x is the number of times line 4 executes, and assume A is a random permutation of n distinct elements. Can you tell me the expected value of x? Looks like it doesn't get any easier than this, right? There's only one thing we don't know about this whole algorithm. Okay. Is there an obvious indicator of random variables here? What's that? Yeah, so if I was going to define an xi, when is xi equal to 1? What's that? Yeah. So it'll execute when the maximum gets updated here during iteration I. Okay, so we have different ways of writing that, but tying it back to the original question, we'll say if line 4 executes during iteration I, and 0 otherwise. And what you're pointing out is that when does line 4 execute during iteration I? Well, that happens exactly if AI is equal to the maximum of A1, A2, up to AI. Right? This happens, when do we update the maximum? Well, if it's bigger than everything we've seen so far, which means it's the maximum of A1, A2, A3, all the way up to AI. All right, so we kind of know where this is going now. Expected value of the sum. All right, expected value of x is the expected value of the sum, I equals 1 through n, xi. Now what? Bring the sum out. I like to say bring the expected value in, but potato, potato. All right. Now we need to go back and look at this thing and hope we can figure out what its expected value is. All right. When is xi equal to 1? Well, when ai is the maximum of these I elements that I've seen so far. What's the probability that that happens? Yeah? No. Here. There's an assumption here. It's a random permutation of 1 through n. Okay, so every number occurs exactly once. Or nothing special about 1 through n except that it's n distinct values that occur in the array. I minus 1, ai plus 1, all the way up to an. And, you know, I say, well, let's not look at the whole thing. Let's look at the front of it here. Well, what is this thing in the front? Well, it's I elements. They're all different. And we can carefully count or convince ourselves, well, whatever they are, they're all different, and every permutation of those is equally likely, which means that the maximum could be here, or it could be here, or it could be here, or it could be here. But there's no reason to think the maximum is more likely to be at A1 than A2 than A3. And in particular, could be here at AI. So each of those is equally likely. So each one must be probability 1 over I. Or you can carefully count the number of permutations in which AI is larger than all of this, and you'll get n factorial over I. So when you then divide by the number of permutations, it's 1 over I. But the point is that the probability that xi equals 1 is 1 over I. That's the expected value of xi. So this is the sum I equals 1 through n of 1 over I. And this sum is so important that it has a name. It's called the nth harmonic number. Yep. Before the what? Oh, yeah, if I mean, here's a question. If you don't believe me that probability is 1 over I, let's define, I don't know, E is equal to the permutations, the set of permutations of 1 through n, so call them A1 through AN, such that AI is equal to the maximum of A1 up through AI. Okay. So this thing you can count, and if you do it, it's not particularly difficult. In fact, you can look in the textbook if you want. The size of this set is n factorial over I. which means that the probability that you get one of these permutations is the size of this set divided by n factorial, which is 1 over I. Okay, so this nth harmonic number is a really important thing. Shows up all of the time. And it's so important that we give it a name, and we also really want to understand what it looks like. And here's something I can tell you about the nth harmonic number. It's not more than the natural logarithm of n plus 1. In fact, it's strictly less than that. But it's also bigger than the natural logarithm of n. So when you see a sum like this, I equals 1 to n of 1 over I, well, it has this nth harmonic number, then that thing is basically the natural logarithm of n, off by 1. In fact, if you want to be more precise, then you can even get way more precise than that, but this is good enough for us. And I think at the beginning of next class, I'll show you where you get this, but maybe you can look at it yourselves. It's because you can bound that sum by, you can show that it's bigger than this integral, and you can show that it's smaller than this integral. I'll show you that with a picture next class. It's easy. All right. It's a good place to stop for today.